Spend 1 hour near a black hole, and Earth could skip years. Time dilation means clocks in different situations tick at different rates. Speed and gravity bend spacetime, so they change how time flows. You will see it not just hear equations today. We ride close to horizons and sprint beside light. We compare clocks on planes, satellites, and mountaintops. Immediate takeaway: time depends on motion and gravity's pull. The rule fits in one line and the pictures explain it. By the end, weird movie scenes will finally make sense. A black horizon fills your window, rimmed by a burning ring. Gravitational time dilation means lower places tick slower than higher places. That difference can separate lifetimes, not just seconds on a dial. Curved spacetime funnels paths so light and clocks take longer routes. Closer to mass, the funnel deepens and clocks crawl. Step away, the landscape flattens and clocks sprint. Picture hovering at 1.5 times the Schwarzschild radius. That is 1.5 times the event horizon radius. Your clock would run at about 58% of faraway time. An hour for you equals about 1 hour 44 minutes far away. Wait a day here, and about 1.73 days pass out there. Fall closer, the factor shrinks towards zero, and time nearly stops. No trickery, just geometry encoded by energy and mass. Lasers slow red near gravity wells, and that matches the clocks. Example in real terms, your sister upstairs would age slightly faster. A supermassive black hole softens tides so hovering could be survivable. So the scene is simple: deep wells stretch time more. You can leave and return to a changed sky. People you know aged faster because they sat higher in potential. Bottom line, gravity's depth sets the tick rate everywhere. Now swap gravity for speed and watch motion bend time. Special relativity says moving clocks tick slower than resting clocks. Time dilation here is set by a clean factor named gamma. Gamma equals 1 over square root of 1 minus v squared. That v is your speed divided by light speed c. It tells you how much time stretches for a given speed. At 0.8 c, gamma is about 1.67. So 1 hour on the ship equals 1 hour 40 minutes outside. Push to 0.95 c, gamma is about 3. 0.99 c jumps gamma to about 7.1. Your hour becomes 7 hours out there, which feels magic. It is spacetime keeping light speed fixed for everyone. Rule of thumb: faster motion means fewer ticks on your wrist. Energy climbs with gamma, so engines face stubborn gains. Momentum also stretches with gamma, matching the slowdown. Inside your cabin, nothing feels broken because local physics agrees. The weirdness only shows when you compare to distant synchronized clocks. We can draw tilted time slices and sloped light cones. Those diagrams encode one rule: all observers keep light fixed. Net result: motion stretches time by a clean, predictable factor. Shift the camera wide across clusters, voids, and filaments. Gravitational potential defines altitude in spacetime, not physical height alone. Lower potential means deeper wells and slower ticking. Astronomy cares deeply because clocks set how we read signals. Light from a cluster climbs out and stretches to redder colors. Stars in voids sit higher and their clocks run quicker. Earth lives in the sun's well and the Milky Way's well. Add nearby clusters and you get a gentle background slowdown. It is tiny here, but precise instruments still catch it. Move from interstellar space to Earth's surface and you lose ticks. The difference is about 45 microseconds per day for GPS altitude. Move to sea level and clocks slow by that same tiny slice. Across the cosmic web, cumulative wells build stranger time landscapes. Galaxy centers crawl while outskirts tick quicker by measurable parts. Astronomers correct for this when mapping expansion and lensing. What to remember: background gravity nudges every timestamp you measure. Back on Earth, we chase nanoseconds with flying atomic clocks. 2 planes circle the world, carrying synchronized cesium standards. One flies east with Earth's spin, the other flies west. When they land, their readings disagree by tiny but real amounts. Eastward loses time from speed, and westward gains time. Altitude adds back time because higher potential ticks faster. Numbers help, so here are famous Hayfel-Keating results. Eastward lost about 59 nanoseconds, westward gained 273. Add gravity and speed carefully, and the totals match predictions. GPS satellites sit high, so gravity makes them run faster. Speed makes them run slower by about 7 microseconds per day. Gravity makes them run faster by about 45 microseconds per day. Net correction is 38 microseconds faster, applied continuously in orbit. receivers correct constantly, or your location would drift kilometers each day. Common mistake is mixing frames, which scrambles these small differences. Engineers keep frames straight so your maps snap into place. Bottom line, applied relativity keeps deliveries and rideshares on target. High above mountains, particle showers rain from cosmic collisions. Muons streak downward, born from pions smashed by cosmic rays. They die quickly, with a proper lifetime near 2.2 microseconds. At rest, they would travel only a few hundred meters, but detectors on the ground count far more muons than expected. Time dilation stretches their lives because they fly near light speed. Take 0.998 c, with gamma near 15.8. Lifetime grows that many times, so distance grows that many times. 2.2 microseconds becomes about 35 microseconds in our frame. Multiply by light speed and you get roughly 10 kilometers. That reaches the valley, so our counters click happily. Tiny test, block the sky with rock and the counts drop. Swap distance for thicker rock and the survival rate changes. These showers are everyday proofs, not just sci-fi theater pieces. Key idea, fast decay clocks stretch, letting short-lived particles travel far. Now hover above a neutron star in crushing blue light. The surface gravity dwarfs Earth's and the space-time well is extreme. Time there runs slow compared to distant interstellar space. Take 1.4 solar masses packed into 12 kilometers. The redshift factor gives about 0.81 for clock rate. 1 hour on the surface equals 1 hour 14 minutes far away. Closer to the center, deeper regions would crawl even slower. Light escaping shifts red, and pulses from hotspots arrive delayed. Astronomers decode these delays to weigh the star and crust. X-ray light curves ripple, revealing mountains only centimeters high. Rapid spin drags spacetime slightly, twisting paths around the poles. So the picture is stark, dense gravity throttles a clock's pace. Slide into a cockpit aimed straight at Alpha Centauri. Thrusters burn hard, then coast at 0.9 c from Earth. The trip needs just under 5 years of waiting. Onboard gamma is about 2.29, shrinking your time. Trip time divides by gamma, giving about 2.1 years. Inside, length contraction makes the distance feel shorter in your frame. That contraction means stars seem closer, along your direction of travel. Acceleration needs fuel, so you split the burn into halves. Halfway, you flip the ship and decelerate toward arrival. You nap, watch movies, and keep healthy with spin gravity. Back on Earth, friends celebrate 2 birthdays without you. Reunion feels surreal because your face looks younger than theirs. Nothing broke rules, spacetime simply rationed your ticks differently. One sentence recap: speed makes trips shorter for travelers, longer for observers. We started with a black hole hour, jumping years on Earth. Now you have the gears, both gravity and speed. Curved well slow ticks and fast motion trims them too. Clocks on planes, satellites and mountains prove it daily. Particles and pulsars turn abstract math into countable events. The universe keeps light steady and lets time stretch around it. So the picture is clear, time is elastic yet consistent. If this changed a movie scene in your head, that is great. Hey, subscribe if you want more clear space stories next week. Thanks for watching and see you in the next deep dive.